Okay, we're going to be looking at fitting factor numeric models, and we're going to use the same data set that we plotted in class yesterday when we were describing the models in mathematical form. So I've just fired up R, and let me make sure I'm in the right working directory. So you should be in the code subdirectory of the course GitHub page. Once you're in there, you should be able to press this button to open up the factor numeric code, assuming that you pulled it from GitHub. All right, so I've already done that. I have it opened up here. So we're going to load in the BGS all data. There is a shortcut. You can load in a data set from a package without loading the entire package. So if you do data BGS all, R doesn't know where this thing is if you haven't loaded in the ALL4 package. But in the data function, you can supply the package name, and this will load in the data. Okay, so we're going to define n as the number of rows in BGS all, so that's 136. If we want to just take a peek at the data set, we can type head. So just to remind you before what we were looking at, the first column is sex. This is one of the columns we'll be looking at for this analysis. There's also a column for height at age 9. This is in centimeters. And there's a column for height at age 18. Those are the three variables we'll be looking at. I'm just going to go ahead and attach this BGS all object. So BGS all is a data frame. If you want to access its columns, you can do BGS all $, for example, sex. That will pull out the sex column. If you get tired of typing that all in, you can attach the BGS all data set. So for example, if I just typed in sex, that object doesn't exist in the R directory. But after you do attach BGS all, now all of the columns are available. So sex, height age 9, height age 18, any of these that we want to work with. All right, so now this is available. The first thing I want to do with the data set is to simply reproduce the plot that I showed in lecture last time. And what I want to do in the plot is just a basic thing. I want to be able to use the color of the plotting symbol to indicate the sex of the subject. So the two colors I'm going to use are black and magenta. And then to create a vector of colors, I'm going to use a little R trick. So the way the R trick works is if I, for example, if I type in 2 colors and I give it the argument 1, 2, this will obviously pull out the 2 colors. But if I were to repeat 1 3 times and then 2, it's going to print out black, 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 magenta. So I can use this sex variable. In particular, if I do sex plus 1, I get 1s for all the boys and 2s for all the girls. And then I can just call callvec 2 colors of sex plus 1. And then this thing will contain the colors. So I don't think I mentioned this, but in the data set, 0 corresponds to boys and 1 corresponds to girls. Okay, now I can just plot height at age 9 on the horizontal axis, height at age 18 on the vertical axis, and set the colors with this callback. And this is the plot that we showed in class yesterday. So here the magenta ones are lower. These aren't labeled here. We could add a legend. Let's do that. So you can add a legend with the legend command. So legend, I'm going to put it on the bottom right. I want girls and boys in the legend, and I'll give it a plotting symbol, and colors are, let's see, girls first, then I have to do magenta, black. So this should add a legend in the bottom right. Okay. Now we're ready to fit some models. The first one we're going to fit is called M1. It just has height at age 9 as a numeric covariate and height at age 18 as the response. So we can fit that with the LM function. The second model we want to fit has sex as a factor. So one way of declaring sex as a factor, so just to recall, sex was this. The zeros correspond to males, the ones correspond to females. One way of declaring it as a factor is just to do as.factor. Of course, I would need to assign this to a new variable. This is just showing the output of as.factor. Another way of doing it, you can do it manually. So that's what I'm going to take here. So I'm going to define, the first thing I'm going to do is define sexfac as a vector of NAs of length n. So we use the rep command to repeat NA n times. Next, I want to fill in sexfac with either male or female, depending on whether that entry corresponds to a boy or a girl in the data set. So the way I'll do that is I'll first extract the elements of sex that are 0. Remember, these are the male entries. So this will return a true whenever sex was 0. And then for those true values, I'm going to assign male. So here, sexfac now has male in those entries. And then I'll do the same thing for female. So this extracts the entries of sex that are 1, which correspond to the females, and this assigns it to females. So sexfac. Now this is not a factor yet. If you want to check whether it's a factor, you can do is.factor. And it's false. This is a character vector at this point. To declare it as a factor, we do as.factor. So I'm going to do as.factor sexfac and assign that back to sexfac. So now if we print it out, this is a factor because it lists the levels here. So what R did is it looked at the entries in sexfac. It determined that there were only 2 possible entries, male and female, and then it created a level for each entry, and it ordered them alphabetically. So female comes before male here. Now we can fit a model, height at age 18 on sexfac, and let's look at the summary. So what this says, because female is level 1 of this factor, and that our default is to set B1 to 0. This number corresponds to the estimate of the average female height at age 18. You can see that looks like it's about right. This number corresponds to the difference between the average male height and the average female height. And that looks like it about makes sense too. Just to show you here, if you have a factor that has only 2 levels, and you have its variable as a numeric variable as 0s or 1s, depending on which level it's in, you can actually fit the factor model using sex without converting it to a factor. The reason is because this is actually a dummy variable. This is a dummy variable covariate. This is the dummy variable for female. And so you can put this into a model as a numeric covariate, and you get the same model fit. So just to show you why that's the same, you get the exact same residual standard error, 6.293 and 6.293 here. The estimates of the coefficients are different. The reason is that this was a dummy variable for female. So this corresponds to the average male height, and this is the difference, female minus male. and so this should be the minus of that number. This is when we declared sex as a factor variable. But it's the same model. Next, we'll fit the factor-numeric additive model. So the way you fit that model is you simply, in the notation, you simply add the two variables together. So we're calling LM, height age 18 is the response, and then the two covariates are height at age 9 and the sex factor. That fits the model. And let's look at all the model summaries and try to interpret the coefficients. So the first one, M1, just had height at age 9 as a numeric covariate. So this number, 32.3416, this is the estimated intercept. So this is should be interpreted as the expected height at age 18 when height at age 9 is 0, which is not really an interpretable quantity. This one is, though, this is the expected increase in height at age 18 for a 1 unit increase at height at age 9. So if you have two subjects, one is 1 centimeter taller at age 9, you'd expect that subject to be 1.035 centimeters taller at age 18. This one we already talked about. This is the M2 is the model with just sex as a factor. And then M3 is the additive numeric factor model. This number is not interpretable. This number is the common slope. So what this means is that if you take any subject and you increase their height at age 9 by 1 centimeter, you expect their height at age 18 to increase by about 0.96 centimeters. So this number is pretty close to the one we got when we just had height at age 9 in the model. And this is the common slope for both males and females. This is the difference in intercepts for females and males. And it's positive. So this is the increase in intercept when you move from female to male. Now we can do F-test to compare these models. Only certain comparisons are allowed. The first thing I want to look at is that if you look at what's printed out at the bottom here, it prints out an F statistic when you do a summary of the additive model, for example. This is a F-test for comparing this model to a model with only an intercept. Sometimes that's a useful test. For this one, we don't think that the intercept model is very good, so we're not going to care about that test. But just so you know, this F statistic is comparing this model to one with an intercept only. One we might compare, what you might care about is comparing, for example, the model with just height at age 9 to a model with height at age 9 and sex, so the additive model. So this does that F-test. And it prints out some information here. So model 1, height at age 18 on height at age 9. And model 2 is height at age 18 on height at age 9 plus the sex factor. This is highly significant, as we expect. Sex matters in height. The F statistic is 392 and the p-value is tiny. We could also compare the model with just sex to the model, the additive factor numeric model. So the model 1 just has sex, and model 2 is the additive factor numeric model. This is also highly significant, which if you look at the data, you can just tell that this is going to be a significant fit. Now the ANOVA function doesn't know how to check if the models are nested. So one comparison that's not allowed is with the F-test is to compare the model with just height at age 9 to the model with just sex as a factor, because those two models are not nested within one another. But you can still run the ANOVA command, and it still does something prints out some residual sums of squares, but it doesn't know to check that these models aren't nested. Next thing here, I just want to make a plot of the additive model. So this is the same plot that we had before. And what I want to add to the plot are the fitted lines. If you want to add a line to a plot, you can use the add-line function. Let me print this out here. Summary M3. So if I want to add a line for the females, its intercept is going to be this number here. So this is the first coefficient. In add-line, the first argument is the intercept of the line you want to add. And the second argument is the slope of the line you want to add. The slope is the second number, height at age 9. So this will add a magenta line with intercept 36.8 and slope 0.96. So this goes right through the female points. To add the male line, the only thing that changes is the intercept. So we have to do the first coefficient plus the third coefficient as the intercept. This is the difference in intercepts. And then the slope is the same, M3 coefficients 2. So this will add a black line for the boys. Next, I want to fit the interaction model. The syntax is very similar to the fit of the additive model. The only thing that changes is that instead of a plus, you do a star. So it's like multiplying these two variables together. But that fits very quickly. If we do summary M4, we see that we now have 4 coefficients that get estimated. So the first one is B00. This is this gets, since R sets the level 1 coefficient to 0, this is interpreted as the intercept for the girls. This is the slope for the girls. This is the male intercept minus the female intercept. Now, one thing that's changed from the previous models, if we look at M3, for example, the difference in intercepts was a positive number under the additive model. And now we got a negative number here for the difference in intercepts. So we'll come back and show why we get a negative number there. And this is the difference in slopes for the males minus the females. So this means that the males have a larger slope than the females. And the male slope is 0.874 plus 0.184. To do the F-test to compare the additive model to the interaction model, we simply do ANOVA of additive model, comma, interaction model, M3, comma, M4. And this will print out everything we need. Model 1, the reduced model, is on the top here. That's the additive one. Model 2 is the full model, the interaction model. The difference in degrees of freedom, so the difference in model complexity is 1, because you add a single parameter to the interaction model. Now, when you have more than 2 levels, this difference in degrees of freedom is going to be larger. So pay attention to that for your homework. The difference in sums of squares, so this is the numerator. RSS 0 minus RSS 1 is 34.4. The F statistic is 2.96, and the p-value is 0.087. So this is not very small. It's smaller than 0.1, but this isn't really extremely strong evidence that we need a interaction model here. One thing to note is that this p-value, 0.08749, is the exact same p-value here for this coefficient. So this coefficient is B12. The reason they're the same is that if you're testing for whether, in this model, if you're testing for whether this coefficient is 0, that's the same thing as comparing the interaction model to the additive model. Because if this coefficient is 0, the only ones left are these three, which are the exact same three that show up in M3, which was the additive model. Now this is only going to be the case when you're comparing factor-numeric interaction to factor-numeric additive when there's only 2 levels in the factor. In general, there'll be more than 2 levels, and you can't do a t-test to compare the interaction to the additive model. But you can when there's 2 levels. Next, I want to plot the interaction model. So this is going to be almost the same code as before. So that puts the points on. For the girls, let's look at this again. Summary M4. So for the girls, the intercept is 48. So that's the first coefficient. So M4 coefficient's 1. And the slope is 0.87. So that's M4 coefficient's 2. And I'm going to make that line magenta. For the boys, the intercept is this number plus this number, so 48 minus 13. So that is coefficients 1 plus coefficients 3. And the slope is this number plus this number. So that's coefficients 2 plus coefficients 4, and I'm going to make that black. So what we said before is that the intercept for the boys is 13 smaller than the intercept for the girls, which doesn't quite agree with our plot, which has the boys line above the girls line. The reason why this number is negative is because we're looking at a height at age 9 range from 125 to 150. The intercept is the value of the line when it crosses 0, which is like way, 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 way over here. And at some point way, way over here, the black line, since it has a larger slope than the magenta line, crosses the magenta line. And the black line actually has a smaller intercept than the magenta line, even though it's higher over in this region of the height at age 9 range. The last thing I want to show is another way of analyzing these data. Many times when you have data, especially when they're positive values, like we have here, it makes sense to take a transformation of the data, and a common one to use is a log transformation. So what I'm going to plot here is the log, and this is log base E, if you're wondering, of height at age 9 on the horizontal and the log of the response on the vertical. See the range here has changed. And I'm going to fit all the same models that I fit before. M5 is just height at age 9. M6 is the additive model, but we're using the logs. M7 is the interaction model, but we're using the logs. I guess I've left off the model with just the sex as a factor. And then I'm going to look at the summary for each of these models. In particular, I'm interested in this interaction model. And what we find here, when we do a test for whether this interaction variable here, so whether the difference in slopes is 0 or not, the p-value is actually much larger. It's 0.248. And we can confirm that by looking at the ANOVA comparing M6 to M7, which is comparing the additive to the interaction model. Of course, you get the same p-value. The reason for that is that oftentimes when you take a log of the response, you're able to break interactions, especially when the values are positive. The reason for that is when you take the log of a product. So an interaction is like a product. So if you take a log of a product, so log of 5 times 6, that's the same thing as taking the sum of the logs. And so you can think of this, this as an interaction model. If you take the log of that, it's like turning it into an additive model. And let's just plot the interaction model here. So this is all the same code. And you see that the slopes are different because the estimate is not 0, but it's a smaller difference than we observed when we did not take the logs, when we analyzed the data on the original scale. And this is a common thing that you'll encounter, that oftentimes when you take a log, you're able to break interactions, which is a useful thing because you would prefer to have a simpler model. So if you can model the logs with an additive model, that's generally better than being able to model the original data with a more complicated interaction model.